Swayam Prabha. Digital India. Educated India.
In the previous lecture, we derived the governing differential equation in an alternative form starting from the virtual work equation and then solved that equation using the Galerkin technique. Today, we will also solve using the Galerkin technique, but in a slightly different way. So, this is what we started previously. We had a governing differential equation in terms of u0 w, and we assumed our u0 as summation of I equal to 1 to m and phi ui q ui, and w was assumed as summation of j is equal to 1 to n phi wj q wj, and then we put this approximation in the differential equation, in both the differential equations, and then we multiplied each of the differential equations, the first by the phi's. So, here what we will do is so there are total m plus n number of equations, there are total 2 equations, and the first equation, if I write it, the first equation is, there are 2 equations, but m plus n number of variables. So, the first equation is E A total del u 0 by del x, and it differentiated plus del w by del x E s total differentiated twice, and then we have minus of del n p by del x plus p x equal to 0. So, what we do is we multiply, and so if I put this u 0 here and this approximation for w here, I get a equation with m plus n number of unknowns. So, I multiply this equation with this phi i's. So, there are total phi u i's. So, there are total m number of phi u i's. So, I multiply it with phi u I times. So, first we multiply with phi u 1 and integrate from 0 to L and equate that to 0, that gives me one equation, and then I multiply it with phi u 2 and integrate from 0 to L, that gives me 2 equation, and so I likewise multiply with phi u I going from 1 to m. So, that gives me total m number of equations. Similarly, I have one more equation, and the equation is del 2 w by del x 2 E s total del u by del 0 by del x plus del 2 w by del x 2 E I total del 2 w by del x 2, and then we have minus of m p minus q z. So, here I multiply this with phi w j. So, there are total n number of j's and likewise integrate from 0 to L. So, that will give me total n equations. So, I get m equations from here and I get n equations from here. Now, in each of these equations, now we shift the derivatives. So, so this is written here. So, it is multiplied with phi u I and all these u zeros and w's are replaced with their approximations. In the previous case, we did not shift the derivatives. So, here we can see that phi u j is differentiated twice. I have a differentiation here, I have a differentiation here. So, comma x means differentiation with respect to x. Similarly, here comma double x means differentiation with respect to x twice. So, here the phi w j has been differentiated 3 times, whereas this phi u I which is multiplied with it has not been differentiated. So, instead of keeping it like that, we shift the derivative and we try to distribute the derivative between this phi and this phi. So, to do this, we do the integration by parts. We have this function phi u I multiplied with this. So, phi u I into integral of this term, that is here, this is the integral of this term inside with this del by del x and evaluated at 0 and L, and then minus the differentiation of this multiplied by integral of this. Here we do the same thing, we take this and take integral of this minus differentiation of this which is here into integral of this. Here also we shift the derivatives. So, phi u I is here integrated and we get n p and we differentiate this and then get integral of this n p, and pi x phi u I remains as it is. So, it is u. So, phi x pi u I remains as it is. Now, if we again look at the boundary terms, we can see that the boundary term vanishes, because at the boundary we have phi u I multiplied by, so at the boundary we have, I mean if we sum up these two terms, this and this, we have phi u I multiplied by E A total into summation. I am not giving the limit in the summation now. Q j plus E S total into summation phi w j comma x x w j and minus n p. Now, this is approximation for u 0, this is approximation for w. So, this term is very close to our n as we have seen before, and again by the same logic that at x equal to 0, my displacement is 0 for the clamped end and accordingly phi is 0, because this is supposed to satisfy the essential boundary condition, and at x equal to L there is no normal force. So, n is 0. So, that helps me get rid of these 3 terms. So, I am left with this. So, this gives me total, sorry, I am left with the rest of the terms and that gives me total m number of equations. Now, we will take the other equation and then multiply phi w I, and again we will do integration by parts and shift the derivatives. So, that is the first term phi w I, this term is integrated once and then we get this minus the derivative of phi w I, and here we have carried out the integration by parts twice, and finally, everything phi w I has got two derivatives and u has one derivative. In this equation we can see that here also we have second order derivative and here also we have second order derivative. So, the integration by parts has been done twice and that gives two derivatives to this w and this phi and two derivatives to this phi. So, the integration by part is done twice here and we get that finally, we get in the integrals we get phi w I differentiated twice, here also we have phi w I differentiated twice, and these are the boundary terms. Similarly, in this expression which we have here also integration by parts has been done twice and these two derivatives have been given to phi w and we can see it here, and this p z multiplied by phi w I remains as it is. Again, if we look at the boundary terms, we see that we have those terms becoming 0. So, the boundary terms is this which has phi w, this which has phi w, this which has phi w, and similarly in the boundary term we have this as phi w. So, if I combine these three terms, that gives me phi w I multiplied by shear force, and they are evaluated at x equal to 0 and L. And again we have the same logic that these phi's are supposed to satisfy the essential boundary condition. So, they are 0 at x equal to 0 and at the other end there is no shear force. So, this is 0. So, this we can get rid of this term and this term. Similarly, if I combine the other boundary terms which is this plus this plus this, and that would give me zero. So, again we apply the same logic at x equal to 0, slope is 0. So, the phi is satisfied to supposed to satisfy this, and at x equal to L bending moment is 0. So, m is 0. So, after getting rid of the boundary conditions, we get the final equations. So, here these boundary conditions are all summed up. So, like I said, we have phi I, phi u I multiply by this. So, this is nothing but n, and here we have phi w I comma x, that is multiplied with this, that is m, and here we have shear v, and that is multiplied with phi w I, and that helps me get rid of all the boundary terms. Finally, we have this equation and this equation. So, here I have m equations and here I have n equations. These equations, m plus n equations, can be written in a compact way as this. Now, please understand, as we defined before, this q vector has total m plus n components. Among them, the first m's are, so among them the first m components are q u, and then we have q w, and then that is equal to F, the force. Q u is m by m, this is m by n, this is n by m, this is n by n. If we look at the ijth expression of q u u, this is 0 to L E A total multiplied by phi u y comma x, phi u j comma x dx, that we get from here. Then q u w, which comes from this term, this gives us q u w I j is equal to E s total, then phi u comma phi u I comma x multiplied by phi w j comma x x dx. So, this comes from this. Now, this gives us q w u. So, we can write it here, q w u is to L E s u s total q w I comma x x q I j comma x dx, and this gives us q w w k w w, k w w I j is E I total phi I w I comma x x and phi w j comma x x dx, and here this is just phi w, x x does not mean anything here, it is not differentiated. Likewise, we can write the forces. So, the force also has, I can say it has two components, two major components. One is F u, which is m by 1, and F w, which is n by 1. So, if we want to write F u I, that is 0 to L n p phi u I comma x dx plus p x phi u I comma dx, and similarly f w I may be written as m p dx plus 0 to L p z comma dx. So, this entire matrix and vectors are defined. By solving this, we can find out q and then we can get our solution. So, here by shifting the derivative, the benefit that we get is the order of the differentiability requirement for phi reduces. In the previous case, here phi had no derivative, but here phi had derivative of order 2, and similarly here the phi had derivative of order of 4. So, accordingly we had to choose phi u in such a way that it is differentiable at least 2 times. Here we had to choose phi in such a way that it is differentiable at least 4 times. But here, because we have distributed the derivatives, in this case, in the present case, the requirement of differentiability is just 2. So, now phi w needs to be differentiable at least just 2 times, and similarly phi u I needs to be differentiable just at least 1 times, and also with this formulation the matrix K becomes symmetric. Now, we will look into another approach, and we can call it Reed's method. It is known as Reed's method. Here what we do is we look into the energy equation that we derived before, or the virtual work equation, and in that equation itself we put all the approximations and get the solution from there. This is the virtual work equation after doing the area integrals. As we have seen, we get it in this form. This form is well known to us. Now, in this form itself we will put our approximations. Again we have the same approximation that we made before. U 0 is equal to I, and W is equal to this. Now, if u 0 is this, we know that epsilon 0 is derivative of u 0 with respect to x. So, we can write this as this. So, epsilon 0 becomes our summation of I is equal to 1 to m phi u I comma x multiplied by q u I. Now, this can be written in the matrix and vector form as this. So, this row vector multiplied by this column vector gives me this. Similarly, kappa becomes j is equal to 1 to n q w I comma x x multiplied by, we are using j here. So, let it be, and j, and again that can be written as this. Then this equation what we have can be written in a more compact way using matrices as this. You can see it if we multiply this column with this row, if you multiply this column with this row, and then finally we multiply everything here, we get this and this, and these are as it is. So, this entire expression is written in a more compact form as this expression. We have defined epsilon 0 and k. So, we can define a vector epsilon 0 and epsilon k, and that can be written in this form. So, if we take the approximations of epsilon 0 and k from just what we did here, and we can combine them and write it in this form. And now, let us give it a name, let us call it a B matrix, and which is of size 2 into m plus n. So, we have B matrix multiplied by this Q matrix, and this Q matrix is the full Q matrix, where the first m number of terms are Q u, and rest of the n number of terms are QW. We can see it here if I just multiply this row, this column with this row, the first m number of terms which are QU gets multiplied here, and then rest of the terms which are QW does not are multiplied with 0. So, on being summed up, that gives me epsilon 0, and similarly here also if I multiply this column with this row, that gives me kappa. So, epsilon 0 k vector is written as B matrix multiplied by the Q matrix. Similarly, let us define another column U 0 W and then write it in this form. So, this 2 by m plus n matrix is called C matrix. So, you are using C multiplied by Q, and that is giving me epsilon U 0 W vector. So, what we have here is this which is written as this, and we have U v, this vector has been written as this. To write this, we have to do some transpose, we will see that, and we have U 0 v which is written as this. Let us give this matrix E A total, E S total, E S total, E I total a name, maybe we can call it a D matrix, and D is 2 by 2. Now, we will rewrite this entire expression in a more compact form, not in a more compact form, but with the help of this B and C. We know that epsilon 0 and kappa, when I write it as a row vector, this will become Q transpose multiplied by B transpose, because epsilon 0 kappa, when it is a column vector, it is B into Q. And if I take variation of this epsilon 0 and kappa, then it will become variation of Q transpose multiplied by B transpose, because B matrix consists of these the derivatives of Q's. So, it cannot be varied, whereas these Q's are unknown to me, it can be varied. So, variation of B is not possible, but variation of Q is possible. So, the variation of epsilon 0 kappa row, this row vector is just this. Accordingly, we have U 0 and W, and that is Q transpose into C transpose. So, we have variation of U 0 W is variation of Q transpose multiplied by C transpose. Now, with the help of this, let me rewrite this expression. So, now we have 0 to L delta of Q transpose multiplied by B transpose, and then we have the D matrix, because if you go back, it is followed by the D matrix, and then we have epsilon 0 k as a column vector. So, D multiplied by epsilon 0 k, which we know as B multiplied by Q, and D dx. It is followed by this term. So, we have minus 0 to L delta of Q transpose multiplied by C transpose into P x and P z dx, and then we have minus 0 to L, the next term is this epsilon 0 kappa. So, that can be written as and then we have the matrix vector NP and MP. Dx. And this is equal to 0. Here we can see that everywhere we have delta q transpose sitting at the front, and again delta q transpose means variation of q. So, the entire expression can be 0 only when we have rest of it equal to 0, because q is an arbitrary variation and their variation of their components are independent. So, if I get rid of this q, we have this equal to 0 to L multiplied by P x P z plus one transpose should be there. So, multiplied by B t m. And again this comes to our the same form that we derived before. So, this is m plus n multiplied by m plus n, this is m plus n multiplied by 1, this is m plus n multiplied by 1, and this K matrix is same as what we got in the previous approach, where we use the Galerkin technique by shift, but we shifted the derivatives. So, the matrix remains same here. And accordingly we have F so KUU, KUW, KWU, KWW, FU, FW, they are same as what we wrote for the previous solution approach, where we had Galerkin technique, where we shifted the derivatives. And again we can solve it and get our Q's, and that completes the solution. With this I would end this lecture here. In our next lecture we will see some problems which we can solve using these approaches. Thank you.